Womp, 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 womp. Look at it. We are at gas laws objective number 3. Yay! All right. So going through objective number 3, it is kinetic molecular theory. So KMT, which we talked about back in kinetics. So that's just a review of kinetic stuff, and then ideal gas law, which we talked about in honors, and then some real gases, which we sort of have talked about before, but not in this detail. So let's go through this as fast as possible. Um, so KMT is a review of stuff. So this is again back from kinetics. So it's just assumptions that we make about the way particles move. Constant random motion. All collisions are perfectly elastic. Volume is of a particle itself is negligible, so it doesn't really exist. And then average kinetic energy is its Kelvin temperature. So temperature is the movement energy a particle has. So KMT basically helps explain all the gas laws. So it explains why Boyle's law changes the way it does. So the relationship between volume and pressure. Charles' law, which is the relationship between pressure and temperature, and then Gay-Lussac's, which is the relationship between volume and temperature. Um, there's some Avogadro's law that's affected in that. Dalton's law, partial pressure is affected by all this. So basically just explains the gas laws as we see them. Um, the distribution of molecular speed, so Maxwell-Boltzmann distributions, we've seen these again way back in kinetics, but it basically just says like, hey, if we have this many particles, if we plot those, some of them are going to be higher speed and higher temperatures than others. Some of them will be smaller, lower speeds and lower temperatures. Um, so it kind of just distributes all the gas particles you have. If the gas itself has a higher average temperature, then you have to stretch that distribution. So you kind of have to flatten the curve, if you will. So here's the general idea. So all of these represent different gases at different temperatures. So if you have the same total number of particles, if uh, the average temperature is lower, if it's colder, that means it's a smaller distribution area. So some of them will be really cold. The average will be right here at the coldest point, um, at the for the coldest gas, and some of them will reach these higher temperatures, but again, the overall average is going to peak really high in this cold area. If we were to slightly increase that overall temperature, we spread this graph out because more particles reach this higher temperature region. So the peak is smaller at the average point. The average point is slightly to the right, and it's here. And then if we flatten this curve out a little bit, we end up with uh, the average being shifted farther to the right. More particles have reached this point over here, really high, but you still have some particles that have low speed and kinetic energy. It's just that more of them are in this higher range than with the colder gases. So same general idea. If we're talking about that in terms of having the right energy for activation or whatever else, that would be like, here's the particles that actually reach the required energy for X, Y, or Z. And so that means that this graph right here that has the highest average, it's the smallest graph because the average gets pushed to the right, but that means it also has more particles that are within this range. Green has more particles than blue. Blue has the least amount of particles that reach this range because it has the coldest average, but it is still overall, some particles do still reach this section. Um, okay, we can look at this in terms of speed as well, because speed is temperature. So if all these gases were at the same temperature, because smaller gases will uh, just due to momentum, smaller gases don't need as much energy to reach higher velocities. That means that the smallest gas is going to have the highest velocity. So these are all the same temperature now, but because helium is the smallest and lightest of these gases, having that temperature would put it at a higher overall velocity. So the heaviest gas is going to be this one right here, which is xenon. Um, and then as you get lighter and lighter, you have more and more particles that now reach these higher speeds. All right, so measuring temperature. Uh, Kelvin temperature indicates the average kinetic energy, so that's that one of those assumptions. Um, so higher temperature means greater motion. So that would mean kinetic energy here is equal to 3 over 2 times R times T. So R is one of those gas constants. R in this case, because it's energy related, needs to be the gas constant that has joules in it. So 8.3145 joules per mole per degree Kelvin. So average kinetic energy is equal to 3 over 2 times R times T, which is Kelvin. Higher temperature, if T goes up, that means this goes up, and that means higher average speeds. So practice using that equation. So calculate the average kinetic energy of methane and nitrogen molecules at 273K and 546K. So I would say you guys should probably pause it and I'll show you guys the answer in a second. There's going to be a lot of these kind of back and forth questions. So make sure you're prepped to kind of try a few practice problems out. But pause the video and you will see the answer in 3, 2, 1. There's your answer. So I'm going to zoom in so you guys can kind of see this a little bit better. So here's that equation that you saw on the previous slide. So that's what we're going to use. Average kinetic energy depends on temperature. At same temp, gases will have the same average kinetic energy. So we just need to solve this out once. It doesn't matter that we're talking about both methane and nitrogen. They should both have the same average kinetic energy. They'll have different velocities probably because they don't weigh the same, but they'll have the same average kinetic energy. So if we're talking 273K, well, 273 times that R factor times 3 over 2 gives us this value right here. So 3.4 times 10 to the third joules per mole. Up here, it says average kinetic energy of these molecules, blah, blah, blah. So we want to know it per molecule, not mole. So for every 1 mole, there's 6.02 times 10 to the 23 molecules. So we cross out moles, and then we get to molecules, so that this divided by 6.02 times 10 to the 23rd gives us 5.65 times 10 to the 23 joules per molecule. And it makes sense that it is a really small number because we're only talking about 1 molecule here. So that's why you have to pay attention to the fact that you're dividing. So at 273K, both gases have this average number of joules per molecule. At 546K, this is what it looks like. So new temperature, same R, same fraction. So we get 6.81 times 10 to the third joules per mole. And then getting that to molecules is 1.13 times 10 to the 28 joules per mole. So higher average because it is a higher temperature. Okay. The root mean square velocity. So this fun equation, honestly, you won't really use this for very much, but we need to show you the equation. So don't freak out that you have to use this all the time, but here's what it is. So this factor right here, the URMS, is the root mean squared velocity, meters per second. So it's equal to the square root of 3 times the gas constant, which is the joules version, times T, which is in Kelvin, divided by the mass of a mole of particles. So the mass of 1 mole of those particles in kilojoules per mole. Or kilograms, sorry, not kilojoules. kilograms per mole. So practice using the average kinetic energy and root mean square velocity. So consider a 1 liter container of neon gas at STP. Will the average kinetic energy, average velocity, and frequency of collisions of the gas with the walls of the container increase, decrease, or remain the same as we do each of these things? So for A, the temperature is increased to 100 degrees Celsius. So is that going to increase, decrease, or remain the same with the number of collisions with the wall? For B, the temperature is decreased, and then the volume is decreased in C from 1 liter to 0.5 liters, because again, we're at STP here in 1 liter container. And then the number of moles is doubled. So we'll look for each one. So try A, B, C, and D, pause the video, all that fun jazz, you know the drill by now. And I will talk through the answers in 5, 4, 3, 2, and 1. So A, we are talking about increasing the temperature. So temperature and kinetic energy are directly related. If temp goes up, kinetic energy increases. Velocity is based off of kinetic energy, so velocity increases. If velocity increases, particles are moving faster, and they are again random, so that means more collisions. Notice how you didn't have to solve any equations to do this. You just are justifying it based off of what all these things mean. For B, the kinetic energy will decrease because lower temperature means lower kinetic energy, which means a smaller velocity, which means less collisions. Done. For C, the volume is decreased to 0.5. So all we're doing is changing the volume here, ignoring any sort of gas law changes that might go along with this. So we're ignoring any like pressure or whatever changes. If all we're doing is changing the size of the container, then kinetic energy stays the same because we didn't do anything to the temperature of these particles. I mean, the velocity stays the same, but it's a smaller area, so collisions should increase. So the particles are moving the same as they would, they just have less space to do it in, so they should collide more often. And then D, same idea. The number of moles of neon gas is doubled, so we didn't change the temperature at all, ignoring any gas law changes. So that means same kinetic energy, same average velocity, but more particles means more collisions. Okay, practice number 2. So consider 2 gases, A and B. Gas A, gas B. Each is in a 1 liter container with both gases at the same temperature and pressure. So everything is identical between these. It's just that they have different masses. The mass here is only 0.34. The mass here is 0.48 grams. So which gas sample has the most molecules present? So which one has the most molecules? Which gas has the largest average kinetic energy? Which gas has the fastest average velocity? And how can the pressure of the 2 containers be equal to each other since the larger gas B collides with the container walls more forcefully? So that's what you guys should try to answer here, and then I'll show the answers here in a couple seconds. So 5, 4, 3, 2, 1. Hopefully you pause the video because here's the answers. So I'm going to zoom in just to kind of separate this a little bit. So P, V, and T are constant between gases A and B. So same pressure, same volume, same temperature. So scrolling down, which gases have the most molecules present? So N is constant since they have the same number of moles and everything. So N is the same between both of these. So that's not changing because it's a constant throughout this whole. Okay. For B, which gas sample has the largest average kinetic energy? Well, they have the same temperature, so same average kinetic energy. So that's constant as well. So last then is which gas sample has the fastest average velocity? Well, the lighter gas A will move faster because if you go back to that earlier slide, light gases don't need as much energy to reach higher velocities. So this right here is our fastest gas. So how can the pressure in the two containers be the same? Well, A is going to collide more often because it is moving faster. B will collide with more force, but the average result is still the same because the total collisions here, while being lighter, will happen more frequently, whereas these will be more forceful but less frequent. So that ends up the same as well. So pretty much everything here is overall the same. The only answers that really show any difference here is that A will move faster because it's lighter, and then the reasoning here is you have to justify it for A and B here. That A is faster but less forceful, B is slower but more forceful, so it balances out. Okay, next practice problem. So average kinetic energy and root mean squared velocity 3. You'll notice that we still haven't really calculated anything at this point. All of this is still based off of explanation more than calculation. So make sure that you kind of think about what's happening before you think about mathematically showing what's happening. So consider 3 identical flasks filled with different gases. So A, B, and C. So we have these different gases. They have different pressures, but the same temperature. So in which flask will the molecules have the greatest average kinetic energy? And then in which flask will the molecules have the greatest average velocity? So again, this is practice. You guys should stop, pause the video, stop and think about this and see if you can come up with the same answer. But the correct answer is going to pop up here in 3, 2, 1. Boom. So we are talking about identical flasks. They are different pressures, but same temperatures. So this is the thing to pay attention to. So because temperature and kinetic energy are the things that are related, all are the same because they're the same temperature. Doesn't matter that the pressures are different, they all have the same temperature. In which flask will the molecules have the greatest average velocity? So now we need to look at their masses. So this guy is the lightest. So since he is the lightest, hydrogen gas has the smallest molar mass. Because they have the same average kinetic energy, he has to be moving the fastest in order to make up that. So this guy has to be the largest simply because the average kinetic energies are the same. He's the lightest, so his response to that is going to be higher velocity. Okay, now then, effusion and diffusion. We talked about this back in honors, and we've probably talked about this at some other point, but 2 terms that we basically talk about once each year and then never talk about again. Diffusion is the mixture of gases. So if you have a gas, how long to diffuse is how long it takes for them to mix. So if I were to spray a perfume in a corner of a room, the amount of time it takes for that perfume to spread throughout the room so that everyone kind of smells it equally, that's diffusion. Effusion is a gas moving through a container wall. So no container is completely sealed. There's always micro cracks and everything else. So if you were to have a gas sealed in a container, a small amounts of it are going to escape from that container. If you think of a balloon, over time it slowly is going to get smaller and smaller and then go flat or basically no longer be inflated to deflate and become a useless thing. That's effusion. It is gas escaping from the container, and so the rate of effusion is really how quickly a gas can escape from a particular container. So different containers will have different effusion rates, and different gases will effuse at different rates. But that's the difference. This is how long does it take to spread across a room. This is how long does it take to escape the container itself. Okay, this brings us to Graham's law, which deals with effusion. So rate of effusion of gas 1 divided by rate of effusion of gas 2 is equal to this right here. So the rates of these two is inversely proportional to the square root of their molar masses. So if we take the formula weights here and square root them, the rates will be inverse of that. So if we take gas 2 divided by the mass of gas 1, square root it, we'll get the rate of gas 1 over the rate of gas 2. So Freon 12 here is used as a refrigerant. It's a kind of nasty thing because it messes with other molecules. So the rate of diffusion of Freon 12 compared to Freon 11 is based off of those molar masses. So the molar mass, so this right here is the rate ratio. So 1.07 to 1. So the formula for Freon 12 is one of the following. What is the molar mass of the unknown gas? Well, here's the molar mass of Freon 11. So we know this molar mass, and we know what the ratio of the two rates is. So the rate of Freon 12 is 1.07 to Freon 11, which is 1. So take a minute, think about this equation, you know, with the two rates, and you know one of the formula weights, so you're solving for the other. I didn't mean to jump ahead, but hey, there's the answer. So here's rate 1 and 2. Here's molar mass 1 and molar mass 2. So we know this ratio, and we know one of these masses. We know that we can assign whichever one we want to be gas 1 and which one we want to be gas 2. We just have to keep them relative. In the problem, it gives us Freon 12 before it gives us Freon 11. So it's probably best to just assign this as 1 and assign this as 2. So that would mean we get this ratio and this fraction. So we're solving for mass 1. If you square both sides, and then you can do some algebra to solve for M1, you get 121 grams per mole. So that would mean we just find which chemical formula matches that. Well, here's Freon 12, CF2Cl2, because as a molar mass, it has the same molar mass. So hopefully that makes sense. I meant to make you guys pause that one, but whatever. Okay, so diffusion, this is where that root squared mean thing comes in a little bit. It also has a similar relationship. So diffusion traveled by one gas divided by the diffusion traveled by the other gas will still give you a similar inverse relationship with the formula weights. Which makes sense. Lighter gases should diffuse faster than heavier gases. So the observed ratio is less than 1.5. Why? So based mathematically, if we look at these two gases, here's the distance traveled by ammonia, here's the distance traveled by hydrogen chloride. We get this formula weight ratio, which is this right here. So mathematically, that should come out to 1.5. Ammonia should be traveling 1.5 times faster or farther than hydrogen chloride. It's not. So observed is less than 1.5 distance. So why is that happening? The diffusion is slow considering that the molecular velocities are 450 and 660 meters per second. And then this tube contains air, and so all those collisions slow the process down in the real world. So this is what you should get ideally, but real world doesn't quite work out like that. So the air in both of these containers, I'm going to zoom in so you can kind of see the container a little bit better. So like this is the glass tube that we're dealing with. Well, these things are moving around randomly. There's air in both these containers, which is colliding, so it's going to take some of that energy change. It will slow these particles down slightly, so you don't exactly see what you would expect. Is really what this comes down to. So this question here, the reason why the observed rate is less than theoretical is simply because of real world conditions. Okay, so that brings us to real gases. So most gases behave ideally until you reach high pressures and low temperatures. So ideal behavior is all of that KMT stuff. They are inelastic, they are elastic collisions, perfectly elastic collisions. Particles don't really have any noticeable volume. They're moving around randomly. They're not attracted to each other, all that fun jazz. If you have high pressures or lower temperatures, well, now you start having attraction forces that start popping out. Some IMF stuff, like we talked about last unit. So van der Waals forces. So the van der Waals equation comes in. You don't need to memorize this thing, but you should know that there's a way to kind of deal with all this and calculate for all of this. So it corrects for negligible volumes of molecules and for what will now start to be inelastic collisions. When particles collide, they will linger with each other for a while because there is some attraction. So there's not going to be a perfectly elastic, there's going to be some energy loss or some redirection or something happening. So in this whole equation here, pressure is increased. IMF forces lower the pressure, so you're correcting for this. And then if volume is decreased, it corrects the container to a small volume. Basically, what we're dealing with here is just that these particles are now lingering and being attracted to each other. So A and B equals van der Waals constant. So this A here is a constant, this B here is a constant. N is still moles for both of these. Volume is both of these. So you're saying this pressure increase, this part right here, you're saying pressure plus all this van der Waals factoring is to deal with the fact that IMS forces are going on, and then the fact that the volume here is decreasing by this Bn factor is to correct the container to a smaller volume because it corrects for this. So, generally speaking, we treat gases as ideal because this is a mess. No one wants to deal with real gas behaviors, and so most of the time we intentionally use gas situations that mean we can avoid all of this nastiness. So gases behave more ideal at low pressures, so generally you keep gases at lower pressures, higher volume situations. Container is very large compared to volume of gas particles. Gases behave more ideally at higher temperatures because they have faster movement, so they don't linger. So they move past each other before IMF forces can really change or modify them in any way. And the smaller the molar mass of a gas, the more likely it will behave. So small gases that have very weak IMF forces, things like helium, for instance, generally behave way more ideally than something that's large and massive and cumbersome and moving slower. So they have smaller the smaller gas particles have less electrons, so less IMF forces, weaker IMF forces, and they won't interact as long. So really knowing what will make a gas ideal or act more ideally is you should kind of have a good idea of what things will make ideal gases more ideal. So Graphical analysis. This is a really good multiple choice question, and I think it pops up every once in a while. So when pressure and volume, so you have this equation here. So this is a modified version of the ideal gas law. Basically, if you take if you take all of the variables and put them on one side, it should equal 1. So if this is true, then the gas is ideal. So all of these gases are at 200K. Note that the pressures where the curve crosses the dashed line is the ideal points. So the times that these gases act ideal is where they are right here, at this point right here. Well, if you notice, hydrogen, hydrogen doesn't really ever act ideal beyond this right here, when it's like basically absolute, or when basically there's no pressure. But at higher pressures, hydrogen starts acting more and more and more, or I should say less and less ideal. At a pressure of about 300 is when nitrogen starts acting ideal. At a pressure of about 400 atmospheres is where methane starts acting ideal, and then carbon dioxide acts ideal at about 550 or so. So looking at this, you might think, oh, well, this is better for everything. Well, the fact is we're talking about pressure in atmospheres. What atmosphere do we normally deal with? Well, 1 atm is standard atmospheric pressure. So if we look at that, that's way over here. So the gas, all these gases also seem to act fairly ideally around about 1 atm. So generally, if you keep things pretty close to normal conditions, standard pressures and temperatures, you end up with pretty ideal gases. If you go to really extreme pressures, these things become non-ideal, and then some of them will cross an ideal threshold again, and then go back to being non-ideal. So it's kind of, you need to pay attention to all the factors that are in that gas. So now we are dealing with just nitrogen gas, but it's at different temperatures. So this curve is for 203 Kelvin, this is for 293, so this is room temperature, and then this is 673, so let's just say much higher than normal room temperatures. Again, all these gases act ideal pretty close to standard conditions, which is 1 atm. Some of them, these colder ones, become lower than ideal for a little bit, and then at these higher pressures go back to being ideal. This room temperature one stays pretty close to being ideal for a good range of pressures here. So from about 0 atms all the way to about 200 or 170 atms or so. It stays pretty close to ideal and then buggers off. And then this red one very quickly stops being ideal. So note that although non-ideal behavior is evident at each temperature, the deviations are smaller at higher temperatures. Okay. So gas laws on the AP exam. With the current things happening this year, I don't know how much this is true, but this is good things, just assumptions for most gas laws in general. Not likely to be asked an entire FRQ problem about gas laws. There's not a whole lot of information in gas laws. It's an honors level-ish topic to begin with, just with a few step-ups for AP. So it's not something that is focused on super heavily. So very unlikely you guys are going to have an entire FRQ gas law problem about this, even more so with given things happening this year. So gas laws are tested exclusively in multiple choice since it's easy to write questions. And so expect it's a multiple choice kind of thing. While in the current year, so in the 2019-2020 school year, that you don't have any multiple choice on the AP exam. So just because the weird things happening this year, this doesn't really apply as much. You will most likely see ideal gas law as one part of a problem in an FRQ. This would be true if you were doing an entire AP exam, with the fact that you guys only have 2 FRQ questions this year because of all the weird stuff happening. There's still a chance, because gas loss is still part of one of the units they said they should be covering, so there's still a chance you'll see something, and ideal gas laws tend to be where you're going to be falling. Notice how we didn't calculate that root squared mean velocity thing at all in this entire note set. Unlikely that that equation is going to be on the AP exam. Understanding the relationship between temperature, kinetic energy, and velocity, and also what gases will have higher velocities, that we focused on quite a lot. So things like that might pop into an FRQ in some way. They might apply it to the ideal gas law, but we'll see. This just gives you a general overview. Any other year, this is all good rule of thumb stuff for gas laws. And hope you'll probably have seen some of this in those practice FRQs. Beyond that, hopefully this wraps up gas laws pretty well, and all the KMT and ideal stuff going on. Other than that, let us know if you have any questions, and this pretty much wraps everything up for you. So I hope that this makes sense to you guys. If not, again, ask questions. Otherwise, have a lovely rest of your day.